ask him for comments. We can ask him to join whatever.
Yeah, I'm open to anything. I guess it depends on how far we get. Or you can even join before he physically gets there. Yeah.
Yeah, yeah.
It depends on, I guess, where we want to take the project or what ideas we have, if we even have any ideas.
I think we have
Um,
ideas.
yeah, maybe.
So, let me show. So, I wish I could have shown you. So, Yulin has done a lot of work. A lot of it has been like he does stuff and then he realizes it's not exactly what it should be and so on. But nonetheless, so you should forget about the titles. These are, I need to show him how to do
That's
titles.
fine.
But what this is this is not what. So this this is, I think this is not Wi-Fi. Wait. Sorry. No, this is this. Yeah. Okay. So this is. Wait. I want to make sure I'm showing you the right plot. This is
Whatever this is, it looks pretty good.
um
With 256
right.
Wi-Fi ensembles, you hit
Right.
the.
Yeah, so like with two, it doesn't do very well. As you increase the number of ensembles, it goes and then it really sits and converges on the theoretical.
Very impressive.
Yeah, so this is good, and we didn't even talk to Sean while producing this, so this is really an independent check. Um, although still with a Gaussian example. Um,
Independent, like you wrote your own, he wrote his own code as opposed to using their GitHub or
yeah,
something.
that's right.
Yeah.
That's right.
Cool.
And there's some like trick. I think initially he was doing the UQ in like the naive ensemble way, and then he realized he has to use these C's. But yeah, once he understood everything, we recovered this stuff, and he's been changing around the Gaussians. It works every time.
Yeah.
It's good. I asked him to like deliberately break it, so like keep reducing the number of training samples until it breaks. And there is a point at which it breaks. That point is not particularly small. It's like 1,000 samples. I think it starts to break already. But yeah, you shouldn't be doing machine learning with 1,000 samples. But yeah, so and I guess that's where it starts to break. Well, we don't know yet exactly why it breaks. The other plot I want to show
Actually,
is
another axis in which to try to break it would be to make the Gaussians higher and higher dimensional, right?
yeah,
You make it
yeah.
like 100 dimensional, 1,000 dimensional.
We could definitely try those things. So this one is the other approach that I was interested in. So you pre-train it on a large data set, and then you fine-tune it on a smaller data set. And then we see that even with Wi-Fi, so naive has no chance here. And then even with Wi-Fi, it's kind of random. Like sometimes it comes close to coverage, sometimes it doesn't. There's no guarantee of anything.
Yeah, this is very telling.
This is
Yeah. And so I asked him to check this a few times, and I think we're confident about this result. And then we showed it to Sean, and he said this makes sense. All the I don't they're not forming a basis, as Ian says. So all the networks are so correlated. So unlike the usual case here, all the networks are built from one network,
Yeah.
one pre-trained network. So they're all correlated. And this again, if we increase the fine-tuning data set, it becomes fine. But if the fine-tuning data set is small, then they're correlated and it breaks. And this is a very realistic setup. So this can and will happen if, and I know people in Atlas who are now trying to do SBI with very little samples, and they're trying to do this they're pre-training elsewhere and bringing it in here.
The setup is that pre-training is so expensive, of course, you wouldn't have a Wi-Fi ensemble of pre-trained networks.
Yeah.
You would just have one.
Yeah. And I mean, that's how foundation models are sold, right? You're not taking like 1,000 pre-trained what is it called? OmniLearn or whatever, or
OmniLearn.
your thing. Yeah, you would take one of your foundation models
Yeah.
So I think this is like what people will end up doing very soon, and they will screw up the uncertainties very badly.
So this is a opportunity, not a
Yeah.
not a brick wall or something. Yeah, so we could come up with something better that could get
Yeah.
back to coverage, then we have a real neat result. We have a real positive result on our hands.
Right. And all of this is with Gaussian, so we will have to redo the whole thing on physics data sets, of course.
Yeah.
You guys have done foundation models, right? So I was wondering if we can pick up one of yours and do an
Sure.
do it.
Yeah, Ian has access to the OmniJet Alpha foundation model.
Yeah,
We'll
but that one is
we fine-tune-
tokenized.
we fine-tuned OmniLearn.
Yeah.
Yeah.
IGN's fine-tuned OmniLearn a
I fine-tune
billion
OmniLearn, yeah.
times now. So
Yeah.
yeah.
I have no experience with foundation models. I mean, I'm sure it's not that hard to be a user.
Yeah, be a user, yeah. Yeah. For physics case though, we would do pseudo experiments still. I mean, how would we get to the z-score threshold of 5?
Um, wait, sorry, what do you mean?
Well, we'd have to go to 5 sigma, right?
Yeah.
Yeah. So we'd need enough data. That's
Yeah,
all? Okay.
we need enough.
So do we
Yeah,
need to
that's right.
do
Yeah,
5?
pseudo experiment,
Do we
pseudo
need to
experiment.
do 5 sigmas worth of pseudo experiments?
We can make it smaller, I think. We don't need five, right? Actually, we only need two.
2-ish, yeah.
Yeah.
So we could do 100 pseudo experiments.
Yeah.
Actually, practical question for people. So Shauna too, when you make this plot and you go to 5, did you run 10 million pseudo experiments to get? Then how did you get coverage probability going up to 5? Oh, you went up to 4?
I think
Oh,
three is
Three.
good. Three is good. We don't need
oh,
five.
okay, I missed that in your plot. Okay, your plot went up to 3. Okay, I see. All right. Yeah, 3 would be totally doable. Like, what? So then, no. What would it mean? What are the pseudo experiments here? They're repeating the whole Wi-Fi ensemble, everything, 1,000 times.
No,
No?
no, I think is you just like I mean, you figure out the Wi-Fi ensembles and everything, and then you just in this one, I don't remember now if it's like per event. So you can hear because it's Gaussian, you can get per event. The whole study is I think per event, so it's very
Mm.
cheap. So for
Mm.
each, yeah, but in our physics case, it would have to become per pseudo experiment. Because we don't have the truth per event, unless we do it with some mat graph simulations where we have matrix element. Then
Mm.
actually we can. That might be cheaper. So is the question of like, do we want to
Like
simulate or
amplitude regression, like what Tillman likes to do, or as the task, or what?
uh, you mean for SBI? Yeah, we could, or we could just do classification and just use the matrix element as the truth.
Oh yeah, yeah. You have the
Mhm.
matrix element plus, I guess, phase space something.
Why?
You need the full probability distribution, unless the phase space cancels out. I guess I don't know.
Right. Yeah.
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 Mm.
So yeah, I think I actually, I mean, my hunch is that like just doing it with MATLAB with matrix elements will be far cheaper.
Yeah.
Um, but like the pseudo experiment one will be closer to what an experiment will do. So there's pros and cons. We can do either. I think it's fine.
Mm.
Because the message will be the same. Like there's a problem. Here's how you fix the problem.
Yeah.
Yeah. Yeah.
Yeah,
Mm.
and I do have some simulations that have matrix element information and has been used for an SBI paper before. We could use that. We could
Yeah.
also just use something else. It's fine.
So does your student have any results yet on ideas for improving this situation?
My idea is to add a new layer, a random layer
Yeah.
to the network. He
Mhm.
doesn't have results yet.
Wait, add a new layer to
So you take a foundation model and you just add an additional randomly initialized layer.
Like a head,
oh,
right? Like a
but okay, wait, hold on. Yeah, let's make sure we're talking about the right baseline. So currently your pre-training and fine-tuning is with, so yeah, in a foundation model, you would normally talk about like the backbone,
Yeah.
the pre-train, and then you switch out the heads.
Mhm.
Okay. You
So
you actually switch out the
fine-tuning,
heads.
yeah, you switch out, yeah, so fine-tuning, you would let the head be randomly initialized, and you might let the backbone move a bit.
I see.
You would play with the learning rates of the two.
I see. Okay. So
Um,
okay, that's I didn't know that. That is yeah. So I think that might work in the cases that at least my colleagues in Atlas are trying, which now I don't have access because I switched to CMS. But they would what they were doing was not so much foundation, more um, their analysis after cuts doesn't have enough data, so they're going to pre-train on like before all the cuts and then
in
fine
that
tune.
case, I mean, I guess there must be a subset of pre-training foundation modeling things that
Yeah.
don't switch out the head.
Yeah,
don't
yeah,
have a
they're
head.
not thinking of switching out anything.
Headless foundation models.
Yeah, I mean, it's just
Yeah.
it's like it's just a pre-trained dense neural network.
But
Mhm.
yeah, okay, so that is a particular pitfall maybe that we could point out is bad. It would not
Right.
cover, I think, most of what the
You're right.
foundation model people are trying right now, which is
Right.
you do give it a head based on your task.
Okay. I think okay. Yeah, so I was not aware of that. So that's good if people are already switching out heads. So we can test that and
Yeah,
probably
let's test
it's
that. That's another foundation model baseline, I think. And
yeah.
then
Mhm. Yeah.
um, and it'd be good to just point out that this is a choice, that you make.
Yeah.
Um, then yeah, maybe just there's other ways to inject more variance into
Yeah.
the fine-tuned thing.
Mm.
Yeah.
Yeah, we can think more about like other ways. So let's just see if it works or not. Maybe with the foundation model, and then I think you were asking about like are these pool distributions Gaussian distributed or not? I think that's interesting. Nobody's looked at things like
Hmm.
that
Hmm.
because if they're not and Wi-Fi still works, that's fine. But that's still something to keep in mind that it might work on one data set, and might want to look at the pool distributions for something else.
Yeah.
Um,
Mhm.
so yeah, I think that would be an interesting set of results and comparisons.
More generally, just finding ways to break the Wi-Fi thing or its
Yeah.
weaknesses, and then there's something to improve on there.
Hmm.
Uh-huh. Yeah. So maybe carrying it out to higher, more dimensions,
Yeah,
see
we
if it
can do
breaks
that.
there. Did they do a physics example in their paper?
They did.
They
Yeah.
only did Gaussians. Oh, okay.
No, they have a physics example of like quark versus gluon tagging or
Uh-huh.
something. Yeah.
Hmm. Of course,
Yeah.
it doesn't, right now, it's very specific to classifiers, right?
Yeah.
Of course, then there's other things you might want to quantify uncertainties for besides classifiers.
Well, yeah, yeah. I think so. I've talked to him about like what about when we do SBI with flows. He says that okay, he has some other paper coming out on that, so I don't want to scoop him.
Oh, okay.
Mhm.
Yeah, but there's a lot that we can do. I think we wouldn't want to grow the scope too much, but like for instance, already propagating these uncertainties into the full SBI pipeline, I think is not fully worked out. Um, like, and that's something. But yeah, to be honest, that's something we are doing now with the HepCC framework. Like we're building this toolkit for SBI. So this is not a paper; it's just a toolkit so that people can do SBI without having to like babysit 10,000 jobs. And
Mhm.
there we're putting in Wi-Fi and we'll eventually want to propagate it. Um, Nonetheless, yeah, the question of propagation is, I think, maybe we should have a chat with Sean together. Like this is something I want to talk to him about. Like he thinks it can be. He obviously it can be done, but how to do it is not clear. Like already the way we did in Atlas, I don't like it at all. Like we did something called the spurious signal method. It's a really stupid way of propagating uh, MC stat uncertainties. These uncertainties,
Mhm.
and CMS does it a different way. But the CMS way also doesn't work very well. So you have these uncertainties. Now you want to propagate them into a final uh, likelihood that includes all the other uncertainties. And I think that is, I think one still has to like show exactly how to do it. But that would be, I think, quite a lot different scope to what we're thinking about.
Yeah, I agree.
Yeah, I think breaking it and just showing where it will work, where it doesn't work, and how to fix those scenarios might be a good enough paper. What do you think?
And is it a theorem from their work, or yeah, generally the case that if you don't do Wi-Fi ensembles, just do the naive bootstrapping, you get overconfident error bars or underconfident error bars?
Yeah, I don't remember. I think they are very polite. So I didn't even see that line the first time I read the paper, where they say that actually naive is not. There's no. I think they say something like it's not. There's no reason for it to work.
I know, but does it always go in the one direction?
In
Um,
our studies, it goes in every direction.
really?
Mm.
It can be the error bars you get could be too small or too big.
Yeah, at least in Yulin studies, sometimes they would undercover, sometimes overcover, sometimes yeah.
I
Also
mean,
depends on.
if it's ensemble collapse, wouldn't that mean you'd always
undercovers.
Which direction is undercover?
Like the uncertainties are too small.
Too
Uncertainties
small,
are too
yeah.
small.
But
Yeah.
yeah, you would think that, but at least in Newland studies, we saw overcoverage quite frequently.
What about you, Shanawaz?
Mm. Yeah,
What
when I was playing around, it was
do you
like
compare?
both. Yeah.
Oh,
Yeah, I was also
Yeah.
surprised why it overcovers so much, and then like as an experimentalist, you can say, hey, that's fine, overcoverage is fine. But yeah, it does overcover.
yeah.
Mm.
Hmm.
Yeah, but the thing is, there's no guarantee. You don't know.
Mm.
Sometimes it undercovers, sometimes it overcovers, and nobody has ever like worried about it. Yeah.
Maybe extending this at least to regression
Yeah.
could be nice. Young classification. I'm just thinking like in our we have these Gaia papers where
Yeah.
we're doing Gaia data analysis and doing the mass density measurement of dark matter. And we are, to get the uncertainties, we are bootstrapping. We are doing naive
Perfect.
ensemble. So our uncertainties are wrong.
Yeah.
Yeah.
It's
But
great.
that's the reason I'm saying, so that's a regression problem basically.
That sounds
Um,
perfect. That
well,
sounds
it's actually a pin. It's actually a pin.
Mm.
Well, no, sorry. The first step is a flow, and then the next step is a pin. So, and I think for both we're doing some bootstrapping. But a pin is yet another thing. Regression is maybe a baby step towards a pin. You know, like a pin.
That's just physics-informed networks. Is that what?
That's like your loss is, so regression would be like you have maybe MSE loss
Yeah.
with a clear target, you know, so f of x equals y. Your loss would be like f of x minus y squared. A pin would be more like you're trying to learn, well, in both cases you're trying to learn f of x, but there's no y for the pin per se. It's more like a differential equation that f has to satisfy.
Got it.
So, but in the end, it's still like some MSE loss for
Okay,
neural
that's
network.
cool. Yeah.
Yes. So I think if we did regression, we would get insight into that case that I personally would care about.
That would be, yeah, that sounds way more interesting than like doing another particle physics example. Yeah, the only
Oh no,
similar,
I'm not saying we touched the Gaia thing directly. I'm just saying if we had,
yeah,
maybe we could, or we come up with a toy particle physics regression problem,
okay.
you know, like energy calibration or something.
So the two places I can think of, obvious places. One is unfortunately is data-driven backgrounds, where like we have used ensembles in the past to estimate those backgrounds. Those uncertainties have even been the dominant uncertainty in Higgs to 4b in Atlas in the past, right? So this is like we claim that this is our biggest uncertainty, and that uncertainty is complete garbage. And it's Higgs. So that would have been a good one. Let me chat with Sean and see if his other paper is going to be too much in the same direction. If not, that could be a
Oh,
motivation.
he might be doing regression already.
I don't know what he's doing. I said data-driven backgrounds, and he said I'm doing data-driven backgrounds with some other.
Okay, but regression as a general task, you don't
Correct,
have to touch data-driven backgrounds.
Yeah, so this one is not regression yet. And then the other one is, I think Tillman and a few others worked with experimentalists in Atlas. So I'm going from like application case backwards.
Oh.
So they showed this, they use Bayesian networks to quantify uncertainties in the calibration. So this is regression and an uncertainty on the calibration. And I think they have like a first paper that's like outside Atlas, and the second paper is inside
Yeah,
Atlas.
this is with Sophia, our postdoc.
Ah, right.
Yeah.
Right. So, yeah, that could be an interesting one. I don't know if they test coverage of their uncertainties. Maybe you could ask Sophia. Yeah, and if they, I mean, I would be surprised if Bayesian networks cover.
Yeah.
Maybe they cover
They're just, Bayesian networks are not so rigorous either, right?
No, not
Yeah.
at all.
Not at all.
pretty random. I mean, my opinion is it's pretty random.
But you're bringing that up just because if we did have something going for regression, then we'd have to compare against them, or what?
We don't have to.
Yeah.
But it's a clear, like if we're talking about regression, yeah, we could either cite your paper. I think that makes sense, and say like we're doing it because like here we're already using it.
We don't have to. I think there's plenty of particle physics things to cite. Yeah.
Yeah. So and the particle physics example would be this one. There are not that many though. Like we don't yet do a lot of like uncertainty on the network stuff. So there are maybe 3 examples in particle physics.
It doesn't have to be like a Atlas or CMS existing thing. It's just like this is something you could imagine doing. Particle
Yes,
physics.
exactly. Yeah, and it's clearly going in that direction. We're using more and more networks, and we want these uncertainties.
Yeah. But yeah, just because like so the theoretical research would be is there a Wi-Fi ensemble type thing for regression? That would be a nice sort of follow-up study based on their paper. And if that works, I guess we could publish it if Sean is not already doing it. And if it doesn't work, then we would have to come up with something even better.
Yeah, sounds good.
So the direct Wi-Fi thing would be you try to regress y, f of x equals y, you get a bunch of different ones, and then you do the same template thing, the same maximum likelihood or whatever.
Something will change because they have this MLC loss that's, I think, a classifier-based loss. So they would have, so they've had to modify binary cross entropy to MLC, and then so for regression,
So regression is always a bit fuzzy, like what is the actual likelihood model? Here, I guess we'd want to pick a first toy example where it really is Gaussian. Yeah, so the likelihood model is like e to the minus f of x minus y squared or something.
Yeah. If you I mean, it sounds like it would be quite valuable to have Sean in these discussions. If you think that's a good idea, I can invite him.
I don't object. Yeah. Okay. I think it would be, given how close this is to his research, it would be weird not to have him in on it.
Okay. Awesome.
Okay. The team grows. So Shanawaz, what are you going to do next? You were, because you wanted to call this meeting because you were wondering what you should do next, right? I don't completely understand the question. Do you?
So I think this is I mean, there's Bayesian networks also. There's some theory behind why they should actually cover under some tremendously strong assumptions. So there are other approaches. This one seems to be the one I find most interesting. There are weaknesses in the theory here. For example, if you see the appendix, they have like this Wi-Fi only works up to like if you have like tiny ensembles, like 16, 32 ensembles. After that, this method itself has a correction factor, which is painful to apply. So that's in the appendix. So already it's starting to break there. So if you if you want to see like weaknesses in the theoretical approach and find a complementary, if that's your interest, maybe you can see that the appendix and then see. But I don't know. I haven't thought about it at all to come up with a completely different theoretical approach to these uncertainties.
Yeah. So you're asking if there's an alternative to Wi-Fi ensembles that's also theoretically grounded and maybe even better theoretically grounded. Is that what you're asking? Okay. Yeah. Well, that goes in the direction of first trying to break this.
Yeah.
That would be the more bottom-up empirical-led approach, is to try to break Wi-Fi ensembles and then see if that guides us to something better. But yeah, one could also read their analysis and think very deeply about it, I guess. without doing any experiments. So concretely, though, I guess it'd be good for you to just make that coverage plot, close the loop on your reproduction of Wi-Fi, and we could see those poles, like how they're distributed, are they Gaussian or not? And then maybe, yeah, you want to just jump on the regression toy example, maybe? Yeah, okay. I mean, to some extent, is the Wi-Fi thing already like regression? Are they regressing the likelihood ratio at the end?
You mean not the training, but the Wi-Fi calibration, right?
Yeah, the calibration part.
Yeah, I think it's a straightforward. Let me. Um, uh, yeah, I'll have to check exactly what they do.
But certainly the initial task is training a classifier. So here you would train a regression network and hope that it
Yeah,
somehow
yeah.
covers just as
I
well.
I think like yeah, what you care about is not like what the ensemble thing is doing, right? It's what the actual task is, and then yeah, they've not. I don't think they've done regression. Let's see.
Yeah, okay.
High dimensional logistic regression. They do mention.
If there was a way to diagnose, well, maybe that's just misguided. Like if you could tell from something about the naive ensembles whether it was going to overcover or undercover.
Right.
Uh, something about like the losses you got when you trained, or I don't know, some diagnostics. But yeah, it must just have to do with how spread out the networks are. Or is there like a infinite data limit where it's for sure gonna over undercover? Maybe at small amounts of data, it's noisy, you get. But if you really had like a lot of data, would it always do one thing or the other? Or have you seen it do either thing even with lots and lots of data?
No, I don't think. No, we haven't done enough studies for me to claim anything like that. And a lot of the results have also been buggy, so I can't trust everything I've seen.
Yeah.
Yeah. In like in our Atlas thing, we had, but completely out of thin air, we claimed that it's probably overcovering rather than undercovering, um,
Mm.
just based on
Interesting.
intuition. Yeah. So
Mm.
no, I don't think I have anything like that.
But regression would be prior dependent, right? So it would be dependent on the labels, like the truth labels that you get, the distribution of the truth. So,
Yeah.
so you might
Yeah.
get an overall like systematic bias because of the distribution of the true label.
Mm-hmm.
How do you deal with that in your pin thing?
We don't.
Okay. Yeah, I have not done a lot of regressions. I've not thought too much about this. Also, for like, let's say the calibration, they're doing a regression, and I think that's exactly the example where like the prior is
What
important.
if you could fix the prior dependence too with the Wi-Fi ensembles, or no?
Yeah,
Or
absolutely.
something.
No, but it's still using a data set to fit the ensembles. I mean,
Mhm.
these are interesting questions we should ask Sean. I can.
I mean, if you could choose, are you saying if you train them all with the same prior, then you'd get something collapsed that
Yeah,
wouldn't
sure.
help?
Mm.
Yeah,
And then yeah, if you, I think it would be a miracle if Wi-Fi
yeah,
could solve that.
yeah. Well, maybe that's like a factorized problem, and you could still solve the coverage, or you say they're intertwined.
Mm.
It has to be intertwined,
It-
I think.
Yeah, if you like have an overall bias, but you have this right size of the error bars, intuitively, I think you undercover. Mm.
Mm-hmm. Mm-hmm.
Right, right. Like yeah, you can't unless you can argue to yourself that somehow Wi-Fi. This is something like Anli and all think about. If you can like train with the wrong prior, and then
Fix
this
it.
calibration you do with the
Mm.
correct data set. Like you split the
Mm.
data set, and then you have like this tiny amount of like realistic data, and then you fix the prior there. Um,
Mm.
and this also like instead of doing it Wi-Fi, you can also just do it with the Neyman construction. Um,
Mm.
but
Mm-hmm.
of course, with the Wi-Fi, it would give you more power than with the Neyman construction.
Mm.
But I can't come up with a easy way to justify that. Yeah, like there are a few stats, even like the other stats people in Minnesota, they pitch these ideas of like, what if you could like train with a bias and then you just quickly fine tune it in a small real data
Mm.
set. But I just don't
Minnesota,
know.
or you mean at CMU?
No, both CMU and Minnesota separately have like
Who are I don't know the stats people in Minnesota.
this is Sarah, I forget her surname.
Oh.
She's really a stats person. Um,
Mm.
and yeah, her student approached me like they're trying to solve some particle physics problem.
I see.
Sorry?
I see. Mm-hmm.
Yeah, but like I don't know how to use it because like I'd never have that kind of a perfectly labeled correct data set.
Mm-hmm. So Ian, are you saying that if Shamanaz goes and tries the regression thing now, it'll just be confusing and doomed to failure because it's prior
Uh,
dependent, or
well, maybe it's still good to try to like build some intuition.
Yeah.
yeah.
Yeah, I mean, people use regression, right? So, like,
Yeah.
they use it in cases where they think the prior is not going to completely screw things up.
Mm-hmm.
Yeah.
So, I
Yeah,
think,
maybe there's a class of priors and a class of problems where the dependence is mild, and so you could still
Mhm.
say something useful.
yeah,
Yeah.
it's
Yeah.
definitely useful.
Okay, well, we can talk more about that here. Yeah.
Mm.
And then, yeah, I guess schedule another meeting with Sean and your student.
Yeah, so he is finally started replying. Maybe he can come say hi and then.
He just woke up. I have to go get lunch and then,
Yeah.
Yeah.
and yeah, so, but yeah, let's talk again sometime. Yeah.
Okay.
Mm.
Thanks a lot.
Okay,
Thanks.
yeah. Thanks.
Bye.
Yeah. Thank
Bye.
you.